Now we're going to use a normal model approximation. So why is that? We have a great formula, it works. But what if there's a large sample? If you're looking, an average poll, when we're doing political polling, has 1,000 participants. And if you're trying to calculate probability of K equals 100, that means you have to figure out how many ways to get 100 with 1,000, right? And well, how many ways are there? So let's just go ahead and put that in our calculator. 1,000 probability, go to NCR for combinations, and then put 100 in. Okay, it's too big a number for the calculator to calculate. So we can't have too large a sample size and use that formula. So is there something else we can do? This is a virtual simulation for flipping a coin. So here it shows one flip and the probability distribution for the number of heads. So for one flip, you would guess you'd either get heads, you get 0 heads half the time and 1 head half the time. If I go to 2 flips, then you get 0 heads a quarter of the time. You can see it here. 1 head half the time, 2 heads a quarter of the time. And as I keep increasing it, you can see the number of heads changes based on the number of combinations we can get. And the shape is starting to get a little familiar. In fact, as I keep going up and up and up, what does this look similar to? This looks a lot like the normal distribution. And in fact, when you're doing a binomial distribution, and this is only with 50 flips, it already is looking very much like a normal distribution. Even if I were to bring it down to, say, 25 flips, it would still look very similar to normal distribution right there. So one of the things we can do is we can actually use a normal distribution to flip the coin, to simulate our binomial experiment. Now there are some conditions on this. If I am doing if I only have one flip, if I'm only doing one sample, this doesn't look anything like a normal distribution. They basically have a rule that n times p must be greater than 10. So when would that happen? When n is greater than 20. And so I'm sliding n up to 20 here. And that works pretty well. Now, if I lower probability, what's going on with the distribution? It's sliding left. So if I have something as low as 0.05, just a 5%, even if I put a big N here, so 50 times 0.05, if I multiply that out, that would be roughly 5% of 50, 2.5 when I multiplied it out. So that's still too small for the normal distribution. What's going on here is that the normal distribution assumes that you can go on forever to the left. And you can see here with the binomial distribution, the least number of heads you can have is 0. Or in our case, successes that we can have is 0. So as long as this product, let's say, let me raise this up to 0.2, then you can see that I've got most of the normal distribution so that it's visible. And that's a pretty good approximation. So we have a general rule that as long as n times p is greater than 10, that's fine. Now it also goes the other way, because if I jump this all the way over to 1, p times n in this case is 50. It's much greater than 10. But the problem is now everything's succeeding. So as I slide this back, I also want n times q to be greater than 10. And so I have to do both checks. The n times p is greater than 10 and n times q is greater than 10. As you saw earlier, when p is in the middle, when it's like 0.5, the normal approximation looks pretty good and you're fine. The issue is when p gets either really low or really high. So why is that? Here I did a sample of size of 10 and p is 0.20. And if I want to use the normal distribution, the thing is the normal distribution is modeling 100% of data under the whole bell curve. The problem is the normal is going to assume that there's going to be data out here because a good chunk of it will be out there. Why is that? Well, here you can see the calculation of the mean when n is 10 and p is 0.2 and the standard deviation. So if I were to use this in a normal distribution, you can see that there is points that should be negative, that right here is less than 2 standard deviations away from my mean. I want to get my 3 standard deviations away from that 0, above 0. So this is actually too low of a value because of that standard deviation. So if my mean were going to stay to be 2, then I'd have to have a standard deviation of like 0.6 for this to work. So let me go ahead and raise the sample size a little bit more, and we'll go with a sample size of 20. So it's getting a little bit better. Here let me scroll down. My mean is 4, and my standard deviation is 1.8. If I multiply that by 3, that's 5.4. I still have a little bit of the tail off over here that I'm losing. So as this comes up, and let me go ahead and go to 50, because when I go 50 times 0.2, then my mean and standard deviation, oh, you can't see it. My mean is 10. My standard deviation is 2.828. 3 times 2.828 is roughly 8.4. So if my mean is 10, most of my 3 sigma is on this side of 0. The same thing applies when you have a high Q. It's just on the, a high Q, high P, and a low Q. It's just on the other side. That's pretty much the same issue going on over here. It's technically, since I'm saying 3 standard deviations, really what I want this to be is, instead of 10, it could be 9. But 10's a nice round number, and that's why we use it. So one more thing, when we're dealing with these probabilities, usually we have to deal with assumptions and conditions, and those are 2 different things. When you are doing your response, you need to be able to state what your assumptions are, and in most cases, for what we're doing right now, it's the trials are independent. Why is this an assumption? I can't verify it. So I can kind of talk through it and say why I think the trials are independent. Now, conditions are required to meet in order to use the models. So we've got the random condition, which is almost always, you're always going to be mentioning that when you do your free response. So you're going to say the sample was drawn randomly from the population. We have to take that as a condition. The 10% condition, so if we're using binomial distribution or geometric distribution, we have to say the sample is less than 10% of the population. And then if we're going to use a normal approximation, this is also called the large counts rule, you need the expected value to be at least 10 and the expected value for failures to be at least 10. So we're at least 3 sigma away from both ends of the graph. And by the way, you're expected to calculate this and show it on your AP test. If you just write NP is greater than or equal to 10 and NQ is greater than or equal to 10, the graders are not happy. Okay, so how can we find probabilities using the normal distribution? Well, if I have a, the normal distribution doesn't really give you the probability of -1 because it's so tiny. So what you could do is, if you're dealing with finite counts, discrete, you could round from say you want a probability of 20. So you could say the probability from 19.5 to 20.5 or 20.4. 20.5 would be fine. So anyways, you could go ahead and do that. Now, we're not going to do a lot of that in this chapter. Mostly you're going to be doing a range of values anyways. And basically, you calculate z-scores and use a normal distribution, as we did in the previous chapters. So here's an example. We're going to flip a coin 100 times. What would be an unusual number of heads? So I've got 100 flips. Probability of heads or tails, if it's a fair coin, should be 0.5. And then my mean then would be 100 times 0.5 is 50 heads. My standard deviation would be square root of NPQ, so it'd be 5 heads. Okay, so 50 is my mean, and I want to know an unusual number of heads. So I'm going to say if you're more than 2 standard deviations away, that's pretty unusual. So we'll check the conditions first before I can use this normal distribution. The 10% condition, have I used more than 10% of the sample? Technically, there are an infinite number of flips. I think we're fine. large counts condition is n times p greater than or equal to 10 and n times q greater than or equal to 10. Well, n times p, that's just mu, which is 50, so that's greater than or equal to 10. We're good there. And 100, we get the same thing, 50. We're fine. So we can use the normal approximation. Remember to write your conditions. So we agree that z greater than 2 for now would be unusual. We haven't really given you a lot of tools for this part yet, but we're going to say greater than 2. So go ahead and calculate the z-score for the x for 2 standard deviations, because this time I'm actually starting with the z. And so I get 10 equals x minus 50 or 60. So that means 60 goes here, which kind of makes sense. If I told you standard deviation is 5, 1 standard deviation, 2 standard deviations, that's 10 away. That would make this 40 and 65 and 35. So anything outside of 40 to 60 heads would be pretty unusual, just using 2 standard deviations or 2 sigma. So let's look at sort of a real-world application. I tried to find an estimate. I know that Lay's potato chips actually inspects truckloads, and they'll take samples. And it's a big deal for quality control for them. And so I did a rough estimate, and a truckload can have around 100,000 potatoes. All right? Isn't that crazy? Assume an acceptable percent of defective potatoes is 5 out of 1,000. So what is an appropriate size range for a sample? So you're setting up quality control for Lay's potato chips, right? And they're saying, okay, we want you to inspect each truck. Okay, so how many samples should I take? Well, on the 10% condition, we need to take less than 10% of the 100,000 potatoes. So our sample size should not exceed 10,000 potatoes. All right, and I really don't want to take 10,000 potatoes anyways. Large count, because then you're going to need more people to count all those potatoes. But I also have the large counts condition, and because my p is very small here, let's see, n times 0.005 must be greater than or equal to 10. So if I divide both sides by 0.005, I get n is greater than or equal to 2,000 potatoes. So that means I need to take at least 2,000 potatoes to use the normal distribution. Why do I want to use the normal distribution? Because I need a lot of potatoes. Now Q is large, so NQ will be much larger than 10. You really should go 0.995 times N times Q times 2,000. And you see, you've got almost 2,000 potatoes. So that's fine. So an acceptable range would be anywhere from 2,000 to 10,000 potatoes. And I'm going to go ahead and play it safe. And let's say I take a sample of 4,000 potatoes. So how many defective potatoes should I expect to find, and what would the standard deviation be, assuming that this is acceptable, right? Well, mu would be 4,000 times 0.005, which would be 20 defective potatoes. And sigma would be square root of NPQ, which turns out to be about 4.46 potatoes. So on average, when I get a truckload of potatoes, I would expect to find 20 defective potatoes, plus or minus however many sigma you want to go on that. So what is the probability that a truck will contain more than 30 defective potatoes? Well, we need to calculate our z-score. We're going to use a normal distribution. I get z is 2.24. So on my normal distribution model, that would be roughly over here. Now, if you're using the table gives the value to the left of 2.24. So I can say the probability that z is greater than 2.24 equals 1 minus the probability that z is less than 2.24. And I actually looked up this value on a table, and I got 1.255%. So we expect about 1% of the trucks that come in to have, let's see, we said 30 or more defective potatoes. So you probably would be rejecting those trucks, by the way. Maybe. It's 2 standard deviations away. It's probably further away than you want to be. So again, you could do this also with your calculator. Remember, it would be normal CDF. And you would basically go 2.24 to like 1,000. And that'll give you roughly the same number. So what can go wrong? We've been doing geometric models, binomial models, and now a normal approximation. So first of all of these use Bernoulli trials. And the requirement for that is you got to have only 2 outcomes, success or failure. All right. Outcomes are independent or close enough. Now, what's a close enough? That is when we're worried about probabilities changing because we took too big a sample. And the 10% condition is the one that applies there. Don't mix up the geometric and the binomial models. They both are based on that Bernoulli trial, but geometric models count for the first success. Binomial models are used for the number of successes. Don't use this normal approximation with a small n. There must be at least 10 expected successes and 10 expected failures before you use the normal approximation.